Hello and welcome to today's video. Today's going to be a second part of playing around with the ATTiny. In my last video I put together a little programmer using the Arduino Nano as a programmer for the Tiny. In this video I'd like to take it the next step further and actually start doing something a bit useful with the ATTiny. My goal is to create a display module using 7-segment displays, but I'd like to put it onto an I2C bus. So my goal is to use the ATTiny as the interface onto the I2C bus, so that will become the I2C slave and have that control the actual display. So with that said and done, let's take a look at my current sketch. So this is currently the state of my sketch, which is to be loaded onto the ATTiny. So if we go to the top, I'm using a library from called ATTiny85. I'll have full details on this, where I got it from and how to download it on my website. So if you're interested in that, please just go into the comment section below and I'll have a link. So I've got downloaded the whitewire tinywires.h library. Currently I'm using a slave address of 4. I just picked that because it's just a fairly unique number. Now the interesting thing is when you get into the pins, so the ATTiny is only an 8-pin package, so obviously 2 of those are one for ground, power and ground for VCC. We're going to use 2 pins for the I2C, which only leaves us 4 remaining pins, and one of those is reserved for reset. If you want to go and reprogram the ATTiny, initially start getting into changing fuse settings, pin 1 is reserved for reset. Now I will probably get into fuses and how to set the fuse and creating a high power programmer to reset fuses, but that's the later date probably. So fundamentally that left me with 3 pins available. And if we take a look at the let's just go and take a look at the 8-bit shift register. Let me just go and take it. This is so this is actually a video I have on the shift register. This was the first start of what I'm trying to do. If you actually take a look, there are 8 output pins really, QA through QH. But to drive it, we have the serial data line, the output enable line, the register clock line, the serial data clock line, and the serial register clear line. So 1, 2, 3, 4, 5. So we've got 5 pins to really control this, and we have 3 available. Now if we start rationalizing this down, if the output enable is permanently tied low, I believe it's low, let me see, output enable, yeah, so the output is enabled low. We can tie that to low, and then that means any data that is set to the output pins of this chip will automatically be displayed. So that's one pin which we can ignore. And then there's a second pin called serial clear, SR clear line, which clears the data from the register within the chip. Now my goal is not to need that. The only thing to be aware of though is when this chip is first powered up or interrupted or whatever, there might be unwanted data in the register, because you can't guarantee what's in there. On power up, it may just be junk. And if the output is enabled, that means that data will immediately be visible on the output pins. So we have to think through a little bit carefully that for the first split second on power up, you may have unwanted data displayed, but just for a split second. There are things which we can do to remove that, and I'll go into that maybe in another video. But anyway, so the minimum lines I'm going to have are the serial pin, the data in pin, the SR clock pin, which clocks the data from the serial pin into the register, and then we have this R clock pin, which latches the data from the internal register to the output. Potentially you can tie the serial clock to the R clock line, but in doing so, every time you pass data in, it will automatically be on the output. Now, I know it'll be very quick, but basically you would see the data entering into the register, and my goal is to actually have a very flicker-free display where the data's in, and when it changes, it's changed once. So I like to have control over the serial line, the R clock line, and the SR clock line. So with that said, let's go back and look at the code. So these are the three lines that I'm going to be using, and the only available pins that I have available are physically pin 2 on the nano, pin 4 on the nano, and pin 2, pin 3, and pin 6. You have to be careful that the physical pin number doesn't actually match the register number. So on the nano, let me go take a quick look at. So if we take a quick look at the nano, this is the pin out, and you can see the registers PB0, PB1, PB2, 3, 4, and 5. Now PB0 and PB2 are reserved for the I2C, which leaves us 1, 3, 4, and 5 is reserved. So that's where we get to the pin outs. It doesn't really matter which one you assign to which. That's almost irrelevant. But this is what I've chosen to use in this design. Now, using this library, if we go to the setup phase, basically on my development board, I have 6 8-bit shift registers, or the 7.HC 595s. And I'm going to use, as I said, these 3 pins as outputs. Now, as I was saying before, I don't have access to clear line or the output enable line. They're fixed. They're always enabled or disabled. Now, what I can do though is initialize the lines so that they're low, and including the data line, the SER data line. And if I, on startup, pulse 8, obviously for 8 bits, times the number of shift registers that we have, I can clock in all 0 into the register. So I can do that, and then once I've clocked in all of the zeros, I can pulse the R clock line, which will then write it to the display of the pins. So if there is any junk data, this will immediately clear the data out. And one trick that I'm going to do a bit later on is this is all done on purely the initialization period of this board. At no other time are we going to be needing to clear random data from the board. Each time we'll be writing new data and displaying it. So the only issue I have is on startup, and with a small little circuit I can actually delay the output enable pin. So if I can delay the output enable by, say, a millisecond, then this startup procedure will have been executed before the output enables. And as long as this is done before that enable pin is set, no junk data will be displayed, and I don't need to worry about touching the output enable or the clear line ever again. So that's my plan. So this is basically just initializing and clearing any junk data from the pins. Then all we need to do to use this tiny library is we set it up with begin with a slave address. The what we're going to be using is 4, and enable a subroutine for the interrupt handler on receive. There's a little bit of code in here to enable sleep mode. Again, this really isn't that necessary, but then we need to enable interrupts. Okay. So what will happen basically is the ATTiny library will sit there waiting for anything to come to its address, and if it does, it will call the onReceive event, which is here. So once it receives any data, this gets called, and all we do is we've got a very simple loop here which basically reads in. So first of all, it works out how many bytes of data have been sent to the chip. For each byte, we will then read in 1 byte. So we'll read 1 byte in. And then for a bitwise operation, all I'm doing is reading the first bit, setting that to the serial pin, whether it's high or low, doesn't matter, that's dependent on the data. And then I just pulse the clock line. With the 8-bit shift register, there is no fixed timing events. Basically, all you need to do is have data available on the clock, on the data pin, the serial pin, and on a rising edge, it will latch that data into the register. And any data that's currently into the register will move 1 place to the right. So because of that, timing isn't critical, but we just latch it in as quickly as possible. As fast as possible. There is no way that the ATTiny is going to go fast or exceed the clock rate that the 7.4 chipset can support. So we can just clock it in. And once we've clocked in all of the data into the registers, once we've done all that, then all we need to do is 1 pulse on the R clock line, and that data should be latched to the outputs, and that should enable the information to be displayed. Now, we do need to be a little bit careful about power requirements. The 7.4HC can handle, I believe, up to like 70 milliamps. Now, potentially, we have the 7 segments and the decimal place or decimal point. So we've got 8 LEDs. And we just want to make sure that with all 8 LEDs on, we don't exceed the maximum capability for the chipset. But that just comes down to what 7-segment display you're using and the resistor that you're using. But it's just something to be aware of. And so you always have to think about the worst case. what is the maximum amount of current that's going to be drawn by the display with everything on. Okay, so we have that. So that's basically the sketch. So what I'm now going to do is I'm going to hook up the Nano, or the little programmer that I've put together. So let me just start this up. Okay, so on my right here, you can see I've got the little programmer. So I'm just going to grab the little ATTiny, and they really are quite tiny. Put it in the programmer. Okay, so we've got the programmer hooked up. So I'm just going to switch over to tell it it's going to be programmed into an ATTiny, check the clock, and check the processor. I'm going to use the Arduino as the programming mechanism, and then under Sketch, make sure you use upload using programmer. The number of times I automatically click upload and I get an error, it's annoying. Oh, one more thing, make sure we're on the right COM port. Okay. 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 That's got it. Third time lucky. Okay, it's programmed and that's fine. So we now should have this sketch loaded onto the ATTiny. Okay, so I just put that on, programmed the ATTiny. I've hooked up this board with the 7-segment displays, with the 6 of the 8-bit shift registers. I have the 2 I2C lines going across to the ATTiny, and I have the 3 pins, the 2 white wires and the blue wire are the data lines which go across to the first shift register. Okay. Okay, so let's see where we're at. So at the moment we have the sketch loaded to the ATTiny, but we don't have anything to drive it. Okay, so let's see where we're at. So first of all, I'm going to do is, if we, in our sketchbook, if we go to the I2C scanner, this is always a useful thing to check every time you're playing around with the I2C, just to make sure, right, tools, make sure we're bored. Okay, we're back to the Nano. If we upload this sketch, so this is just the wire, the I2C scanner. Okay, I see what I've done. Okay, it's important to have the ground actually hooked up. Okay, so once we've actually powered up the device, we can now see that we have it's found at address 4, which is what I wanted. Whenever you do a demonstration, everything is always guaranteed to fail. Okay, so now I can know that I can communicate with that. Let's go back to my sketch for displaying. So in this sketch, this is basically just setting the I2C address to 4. This is the master, so this is on the Nano. And I'm just going to write some data. So in this situation, I'm writing 232 decimal place 1. And then my goal is to use this potentially as a temperature reading. So what I've done is define like a little O is like degree, and then capital F Fahrenheit or capital C for centigrade. So in this sketch, all we do is we use the wire interface. We pass in the slave address, and we just go through this char array, and we send through the appropriate value. So let's see what happens. Okay. Okay, so the sketch compiles, it's uploaded, and we get a load of junk data written to the display. Okay, so I'm back again now. So we're having trouble trying to figure out why the data wasn't being displayed correctly on the 7-segment displays. Finally figured it out. It was just a small case of I'd not connected the power to the chip. So it's actually an interesting issue that even without the VCC line connected to all of the 7.4 series chips, we can still see the output sometimes, but it's just junk. So let me just show you what was going on. So basically we had that situation where no power was being connected, and 4, 5, 6, 7. But we were seeing random things appear on the output. As you can see, no power connected to the VCC pins, but we still managed to get an output. This is a perfect example that if you have unused pins on any of the logic devices, you don't want to leave them floating high or floating low. You really should tie them high or tie them low with a resistor to prevent them going through random events. In this situation, it just turned out that even without the VCC lines coming through, we can still get power coming through to the output, which is completely undesirable. So I've now reconnected power, but now you can still see that we have junk data on the output. And this is a perfect example of where you want to make sure you know what's being displayed. So if we change this code now, 1 2 3 4 5 6, upload. So I'm now loading code. So we upload 1 2 3 4 5 6, and as you can see, it's a bit hard to see with the wires in the way, but we get the right things displayed. Now this is where I was talking about potentially making this into a display which can display things like date, time, temperature. So you can see, like, I have a 0F. It's a little bit hard to see with the lights, but you can see. I'll push it out of the way. So we have like degrees F. So my goal is to make this a display, a flexible display, so we can get rid of that junk now. We don't need that. So that's the first phase of getting this working. So from an I2C point of view, all we need to do is basically pass in, say, 1 2 3 4 5 2 2 decimal 3 1. So we can pass in any decimal number, and 1 2 2. You can see the decimal point is being lit in the right location. Okay, so anyway, so that's the idea of this. See. Okay, so we do have a little issue. For whatever reason, the decimal C is not coming through correctly. It works fine with all of the 2 3 4 5 6. We did that one. Let's just do. So it looks like I'm passing through all of the data correctly. 6 5 4 3 2 1 here. I've just got a little bug with my decimal place. I just need to figure that out. Anyway, I'm going to do a bit of work on that and get back to you. But in my next video, there's a couple of things I want to improve this on, or improve this with. We have the ability to set, obviously, whatever we want to display. But at the moment, the ATTiny has one I2C address. And if I wanted to have multiple of these boards connected, I would need some way of changing the I2C address. So my plan is to put in a little, some registers basically for the I2C, which we can set through the I2C bus to enable us to programmatically change the address. So I'm going to do that in the next video. So if you're interested, please stay tuned. Otherwise, thank you for watching. And if you have any questions or comments, please leave them in the comment section below. It does help a lot. Thanks very much for watching. Bye for now.